To the coffee break, which hopefully has revived some of you. So it's my pleasure to introduce our next speaker this morning, who is Alistair Forbes from the National Physics Laboratory. We have started engaging quite substantially with NPL over the last year. I would say we have a joint case studentship with NPL, as well as a fellow who is going, a postdoctoral fellow who is going to join us in March. And so I'm quite excited about this, and also I look forward to Alistair's presentation today, which is about measurement traceability and new measurement modalities.
Thank you, Caroline. Thank you very much for the invitation to be here today. It's been very interesting for me already. So I work at the National Physical Laboratory. We're what's known as the UK's National Metrology Institute. And there are about 750 of us in Teddington, southwest London. So these are laboratory space that we moved in the early 2000s. I work in what is now the data science group, but it used to be called the mathematics and modelling group. And so I don't know if that's progress calling it the data science group or not. But let me just sort of summarize why the government funds us to do research in metrology. Well, we're responsible for maintaining standards or developing standards for units of measurement, and according to the SI there are 7 base units: a meter, kilogram, second, ampere, and so on. And we're responsible for primary realizations of that, and in that sense we're responsible for providing the most accurate measurement possible for the UK. So for instance, for the meter, that's defined in terms of laser interferometry, and typically we can get accuracies of 1 part in 10 to the 12 for the meter. The kilograms, one of the few artifact-based standards of units. It used to be the meter was a chunk of metal so long. The kilogram is still a chunk of metal kept in Paris. Time is defined in terms of an atomic clock, a cesium fountain clock, and there we're getting accuracies of the order of 1 part in 10 to the 15. But we are hoping to replace those with a single trapped ion clock, where we've just got one ion trapped in an electromagnetic trap, cooled down so it's hardly moving. So any transition photon has a very, very fine fixed frequency, and that will allow us to do measurement in about 1 part in 10 to the 18 for time. So that's 1 second in the age of the universe. The Kelvin at the moment is defined in terms of the triple point of water. That's a point where water exists as a solid, a liquid, and a gas, which is reasonably accurate. So you can generate, you get little cells that generate triple points. But water is quite a complex substance. So in 2018, next year, we're hoping for a big change in metrology, that the agenda of making the units related to fundamental constants of nature will eventually be realized. So we're hoping to replace the kilogram by relating mass to Planck's constant, and replace water, the Kelvin, by Boltzmann's constant. So that's how we'll be able to relate units of measurement to fundamental constants of physics. And the idea being that everybody has access to those. You don't have to take your kilogram and compare it to the one in Paris. So that's one of the things that the scientists at NPL gets involved in, is trying to figure out how we can access these fundamental constants in a way that we can realize them at very high accuracy. The other thing we try and do is develop these traceability chains, so that there's a chain of measurement from the kilogram in Tesco's to the kilogram in Paris. And that's an undocumented unbroken documented series of calibrations. So that step, that chain, is unbroken. So you can relate the kilogram in Tesco's through various calibrations to the kilogram in Paris. And each of those calibrations got a stated uncertainty. So uncertainty is very big in metrology. No measurement can be complete without a statement of uncertainty. And these days we talk about knowledge about an artifact, and our knowledge about a system in terms of probability distributions, and the estimate of that quantity is the mean of a distribution, and the uncertainty, the standard uncertainty, is the standard deviation of the distribution. So a lot of our analysis very statistical, very probabilistic. However, we tend to make simplifying assumptions in terms of normality and independence, unbiased and linearity of systems. But we've been doing this sort of stuff for over 100 years, and collectively the National Metrology Institutes have provided confidence in measurement, and we do that by investing quite a bit of effort. So we've got an organizational structure. There's the Bureau of Weights and Measures in Paris that sort of oversees the whole of metrology globally. There are various consultative committees. These are guys that are looking after the meter, looking after the kilogram, trying to figure out what's the next best bet for a redefinition of one of these units. There's the Joint Committee for Guides in Metrology. So as well as the standard units, we also have agreed experimental procedures, how these units are realized, and we've also got an agreed vocabulary, the International Metrology Vocabulary. So these are all activities that we've done over 100 years or so to make sure that we're all using the same language, we're all doing things in very similar ways. We also have an agreed methodology for this uncertainty evaluation, so when people make a claim their uncertainty of their meter, and they're using a standard approach. And we also make sure that we do experimentation to make sure that when we say we've measured something to a specific accuracy, we can test that by using various interlaboratory comparisons. And these results are published and made available in a database so people can see how various laboratories have done in various exercises. And with that sort of level of investment, we can clap ourselves in the back and say we've achieved a very high level of reproducibility and interoperability and trust in measurement. And that's led to global manufacturing. So we can assemble parts from different parts of Europe in particular, but other parts of the world. But also over time, we can compare measurement of sea temperature now with measurements we made 100 years ago, because we've got a common frame for those sorts of measurements. So a lot of the work we achieve very high accuracies by doing everything in the laboratory, and we tend to have a single system, single instrument measuring a single measurand, the length of an artifact. It tends to be a static system. We get our accuracies by getting rid of all the environmental factors, so we've got very close controlled environmental conditions to 0.1 degrees in temperature usually. Our systems are simple. They have a modest number of degrees of freedom. Our instruments are designed according to well-known physical principles, so we know exactly how the instrument's going to respond. And we don't need a lot of data. If we were just measuring a single quantity, we just essentially maybe need one or two pieces of data. And the sort of computational tools that have been used in the laboratory over the last 100 years are reasonably straightforward. Fitting a straight line to data is still a standard activity at NPL. So it's optimization model fitting. And we use the uncertainty evaluation methodology. We use a simple propagation methodology. So if you've got uncertainties associated with inputs, you can calculate the uncertainties associated with output. But increasingly, our government departments are asking us to say, look, what can metrology offer the world in terms of addressing some of the societal challenges to do with health, life sciences, environmental monitoring. And in those situations, the measurements are done outside the laboratory. So you may be using networks of sensors to measure air quality, for instance. You may be measuring at different locations, you may be measuring different chemical species where you're measuring air quality. The systems tend to be dynamic. You're not in laboratory conditions. You may have a system, it involves a very large number of degrees of freedom, and you're maybe using a lot of data. Our models, we know what some aspects of the system are doing. We may know something about how the sensor behaves, but there are other aspects of the system we don't know. So maybe we can use data to learn about those other aspects. And so the computational approaches we use are more to do like data assimilation. We're starting to think about using machine learning, statistical learning, I would say more, And instead of uncertainty propagation, we're using a sort of more generalized uncertainty quantification, where we're not only looking at the experimental uncertainty, which is to do with random effects, but we're also looking at model uncertainty. So if we've got partially understood models, we can't assume that the model we put down in our paper or written into our code exactly reflects what's going on in the world. So there will be an uncertainty associated with the model. We may be using approximate models, or we're using surrogate models for models that are very expensive to calculate. But we've got various tools that we can use. So we can, if we've got a number of plausible models, we can consider each one, which one fits the data best, and select the one. Or we can average over the plausible models. We can augment an existing model by some surrogate model or a Gaussian process or something like that, which allows the data to have maximum choice of telling us what the system's doing. And we can go through some various validation exercises. Model uncertainty tends to be a large contribution, but at the same time, it's also the opportunity to reduce uncertainty. If you've got a model that actually does reflect the physical system, then you can extract more data and more information from the system. So modeling is really quite often key in getting the sort of accuracies that we're looking for. There's also the algorithmic uncertainty. We're dealing with large systems, large amounts of data. We've got algorithms to try to find something, extract information. And they may be approximate. They will, if it's nonlinear, they'll have convergence tolerances, and so on and so forth. So the uncertainty to do with the algorithm is an important feature of what we're doing. And also writing in software, maybe the software is has been written incorrectly, or implements that numerically unstable algorithm. And even today, we find packages from major suppliers in science that are producing software that does some optimization, and the performance is extremely poor. Instead of getting accuracies of about 1 pound 10 to the 12, which you might expect, we're getting accuracies of worse than 1 pound 10 to the 3. So there's a lot of tools out there that we think are working well, but in fact are working quite poorly. So another aspect of, sensor networks is becoming a very important way of how we sort of learn about the real world. So one area we've been involved in NPL quite a bit is in air quality networks. So there are various global networks looking at various sites in the UK, tracking the levels of these PAHs, as polycyclic aromatic hydrocarbons. And the European Union has mandated that we must, as a nation, monitor these. And there's a whole list of different gases that we must monitor. And again, the directives from the European Union say you must have some aspects of data quality. You can't just measure these things and just accept them. You have to demonstrate that you're measuring to a certain precision or a certain uncertainty. And there is also this requirement that those measurements must be traceable back to the mole. So again, these measurements can't be ad hoc measurements. They have to be well designed, and data analysis coming out of them has to be proved to be providing useful information. So one of the things that we do is there are a lot of manufacturers of different sensors for NO2 sensors, the diffusive samplers. So are these systems working well in practice? So what we can do is have co-location studies where we have a number of sensors from different manufacturers in a one place, also co-located with a reference sensor, and we use a reference sensor to monitor how well these other sensors are behaving. So this photograph here, I think, is in Marylebone Road, which is very well studied. It's quite a well polluted road in London. One of the things we're also interested in, some of these air quality sensors work on chemistry, and that's quite tricky at times, and it's quite expensive to do the analysis. If you can measure the color of something, so how black it is, then perhaps you can use that blackness or black carbon as a surrogate for these expensive air quality measurements. And we see in different places in the UK, there's quite a strong correlation between the black carbon and the pH measurement. In other places, not quite so much. But surrogate measurements is something that we're very interested in because we may be able to sense a lot more cheaply. Acoustic noise is another aspect that the EU mandates that we measure, or at least develop sound maps. And quite often these sound maps are developed on the basis of models, but we're very interested these days in actually measuring those. Living about 8 miles from Heathrow, air noise and pollution and the like is extremely very noticeable and has an effect on the nation's health in terms of stress and the like. There's also mandates to measure marine noise and the noise generated by man in the ocean due to ships or due to piling. When we're constructing these offshore wind farms, it generates a lot of noise, damaging mammalian life, for instance. So we have sensors of hydrophones all over the North Sea measuring noise, and we're trying to interpret or trying to find out, is the noise getting worse or are we improving things? So there are various issues about how we provide confidence or ensure confidence in sensor network measurement. So there's a standard things we can do as a laboratory. We can look at the sensors and see how they behave in the laboratory, and we can calibrate them, things like that. But so that's what we know what happens to them in controlled conditions. But what happens when you stick them in the side of a bridge or the side of a building? There's an issue about where you place those sensors. In experimental design, if you've only got one instrument and one artifact, it's very straightforward. If you're trying to measure a map or determine a map, where you sample and how you sample is quite important. So there's a macro scale issues about how you spread the sensors to be representative of the things that you're trying to measure. And there's also various sort of micro scale things. Are you happen to put your sensor in a very atypical environment? It may be that environment is changing. If there's trees and things going around it, that environment will change over time. And if you track that change, are you tracking something of interest or tracking something that happens to be circumstantial? We may want to put in reference networks. So for instance, in London air quality, there are about 110, 120 air quality reference sensors, and they cost about £5,000, quite expensive to maintain, but they are giving good information at those points. But can we supplement them with low-cost sensors that maybe cost £100 and have them placed in where they happen to be placed? So there was a few projects to put them in schools, in school buildings, have the school kids see how the air quality has been measured there. But there you happen to be putting them at schools. Is that representative? So and can you use reference network to calibrate these low-cost networks? And then there's all the issues about how you extrapolate the information, or you extract information from the sensor networks. If you're talking about the mean pollution in London or another city, how does that change if the network is also changing? So you're sampling at different points. If you happen to be sampling more at a more polluted part, have you taken that into account when you're saying whether or not the pollution is getting worse or better in a particular area? Very interested in multimodal sensing as well. For instance, a lot of things that pollute also make a noise. So can you just listen to the traffic noise and get a sense of how much air pollution is being generated? We know that different types of vehicle will produce different types of pollutants. They will also have a different sound signal. So can we do some interesting diagnostics on the basis of these multimodal sensor networks? But I think at some point, whenever you talk about multimodal sensing, you have to remember there's a specification on sensing because you're not measuring the same thing. You may be pointing the sensors at the same object, but they're measuring different aspects of it. So correlating those two things has to be done with a little bit of care. So here's examples of 5 urban sensors in London, and they happen to be in park areas over a week. So this is 7 days work, and they're measuring NO2, and you can see the sort of bumps to do with the this is Friday afternoon, so that's the sort of rush hour on a Friday afternoon, and then tails off on Sunday. Nothing much is going on at all. But one of the striking thing is that although these sensors are kilometers away from each other, they're all picking up essentially the same sort of signal because it's an urban background. So the fact that different sensors are saying finding something similar means that you can calibrate one group of sensors against another under the assumption that they're both seeing similar signals, in sort of various experiments we've done to show that this can be done very effectively. So the other new modality that we're very interested in is imaging. And it's used across all sectors, so Earth observation, health, and so on and so forth. And quite often, again, there's this issue about modality. We might be measuring somebody with an MRI and a CT scan or a PET scan. How do we stick those together, knowing that we're measuring different attributes associated with that person? So in industrial inspection, we've got an XCT system at NPL, and as a measuring instrument, it's really quite complex. So you've got many subsystems, each of which is complex. So you've got the X-ray source itself. Now, so the beam won't be completely homogeneous spatially or temporally. It will be drifting. You've got a detector array, which will be manufactured to a specification, but it won't be ideal. There'll be various sensitivity changes. The fact that it's operating in a temperature that's not held totally fixed means that the source and the detector will be changing its relative position. You've got a spindle system that rotates the artifact round. That will not have a perfect alignment. It'll have a wobble. The refract, so these are all geometric things that we can sort of handle quite well with the sort of uncertainty methodologies that we've got. But we've got the various reconstruction algorithms, solving an ill-posed, ill-conditioned inverse problem. So they will have a big effect on how you map the absorption in that volume. And then once you've got that map, you want to do some thresholding to say when the different materials change, when you go from air to a material. So you want to find out something about how well that part has been made in an additive manufacturing process. For instance, you want to say exactly what's its shape, and that means that you need to determine where the threshold is between the air and the material. So that thresholding algorithm will have a significant uncertainty. And in general, if you're doing feature extraction, you've got all these classification algorithms that you need to look at. Okay. So the reconstruction algorithms, as I said, you're solving an ill-posed inverse problem. So you, in order to make it better posed, you apply some regularization, which may be based on lots of different things. If you're using a Bayesian approach, you'll be saying something about some prior distributions, what you expect to be there. And you've got all these ideas, well, what is the effect of different priors or different regularization on your reconstructed map? What's the uncertainty quantification with that? If you change the prior by a small amount, do you get a significantly different reconstruction? But again, if we get the prior information correct, then in the sense that the prior information is reflecting the actual physical system, then you can extract a lot more data out of it, a lot more information. So this business about model uncertainty or information gain, we said the uncertainty is your opportunity to improve the system. We've had a bit about machine learning this morning already, and our customers, our clients in the industry, our clients in the health services are extremely interested and they want to use these things. But if they're using them for discovery, if they're using them if I use them to find my car keys, I'm happy if I found my car keys. But if I'm using to control a car or control a nuclear power plant, so it's a different sort of risk. And so people are saying, look, can we, if we want to have confidence in information that's been extracted using some machine learning algorithms and the like, can we quantify that uncertainty? So there's accuracy of training data. If it's the supervised learning, if it's the correctness of the labeling of the data, very importantly, the representative of the training data. If you happen to be training on just the data that happens to be around, then is that representative? Loss of information due to dimension reduction and the uncertainty associated with various classifications. We saw a beautiful example this morning about the panda and the gibbon. A small change in their training data, innocuous change, and you get a totally different result. And people will be worried about that. And so, the sensitivity analysis, what training data is driving algorithm, what changes to the training data can you make and still get a decent result, or what changes can you make and get a totally different result? Could you have training data that's actually meaningless, but actually ends up with the same classification algorithm? So again, in terms of reproducibility of results, there's a lot of interest in literature and the press and things like that about whether or not scientists are doing a useful job or not. Or they just writing a lot of papers that nobody can reproduce. So that's an issue. If your results come from a machine learning algorithm, how do you make sure that in some sense it's reproducible? Can you get to that state that the machine learning algorithm was at the time it made that decision? And again, there's a issue about, again, coming from EU directives, about the explainability of decisions. If you're making a decision that's affecting somebody's life, if you're turning me down for a whole pile of for a loan or whatever, and you're making that decision on the basis of machine learning, can you explain to me why I didn't get the loan? And if you have no idea what's going on in your machine learning algorithm, I don't think you can do that. So those are all issues that if we're going to use these new measurement modalities and then these new data analysis methods, we have to address if we're going to bring them into a framework where into a metrology framework or into a framework of confidence or a framework of trust. And NPL sort of trying to invest a little bit of our research effort in collaboration with various universities. So as Carola has just said, we will be appointing somebody in March to work on quantitative imaging. How can you get quantitative results? The size of the tumor, traceable to the meter from imaging. We have a PhD student who started earlier on in October, I think it was, and using machine learning for spectral imaging applied to agri-tech. So Philip's just there in the blue. So that's exciting for us because it's very interesting. And we've got various other PhD studentships looking at different aspects of sensor networks or Earth observation and the like around the UK and elsewhere. Lots of European collaboration in that area and collaboration with the US. So there are quite a few challenges ahead from a National Metrology Institute. We are about providing the most accurate measurement, and by doing that we can see further, and we can find more. We can find stuff that nobody else can find. So that's very exciting. There's this issue about how metrology can help reproducibility as scientific research by providing that ground truth. And there's also the fact that we're trying to use measurement to address real problems that the world's facing, and there are quite a few of them. There's this notion that there's a balance of uncertainty contributions. For the high accuracy of measurements that we can do in the laboratory, it's really trying to make sure that model uncertainty and algorithmic uncertainty don't come into it, because it's very difficult to quantify. But for real world applications, we have to embrace that. And we're trying to do that by using, for instance, networks of sensors and trying to address various imaging issues to do with making imaging a quantitative science or precision science. And I think down the line, we, the National Metrology Institute, will be investing quite a bit in trying to put that uncertainty quantification framework for machine learning or statistical learning. And there's also this issue, I think, that our customers are asking us, say, look, can I get some sort of indicator of the quality of a piece of data? Can I say something, a kite mark, or a data readiness level? You know, is this data only to be used for your own sort of just poking around, or can it be trusted to build a system on? So it's giving some sort of level of confidence. I think, you know, our customers are asking us to do that, and we don't know how to do it. And I think, you know, with the institute here, the Institute of Mathematics for Information, or Mathematics of Information, you know, is well set up to address some of these issues. You know, so we do look forward to the collaboration here and with others to address some of these issues. Thank you.
Thank you very much. Questions?
I have a question about the use to which the information you provide is put. Clearly, you've described very clearly the challenges of assuring the quality and knowing the uncertainty in the measurements that you make. I wonder if the users of that information are well plugged into the uncertainties that they're provided with.
In the engineering community, which is traditionally been our application domain, I would say pretty much, you know, that they understand what a calibration certificate means, and it's just, this is a length and this is uncertainty, and they use it appropriately. If we're starting to talk about far more complex systems, there's an issue then, what do you actually put on the calibration certificate? You know, do you put in, you know, can you put in 10,000 samples from this posterior distribution? And how on earth would the user use that? So you know, that's part of the challenge, I guess, is for the Metrology Institute to provide that ground truth, but in a way that the users, the client communities can use sensibly and effectively. So one of the things that we're talking about these days is not only confidence in data, but it's the effective use of data. You know, how can you present information to people in a way that they can use it appropriately? You know, usability of software, for instance. You may have a fantastic algorithm, but if you keep on plugging in the wrong input parameters, you're going to get rubbish results out. But it's nobody's fault in a sense. But you know, that is still a contributor.
Talking about sort of data information or kind of running information, do you share a lot of these data with your other national institutions?
Yeah, so some institutions are better at it than others. So a lot of the national metrology institutes have what they call standard reference data. And one of the initiatives that we have at the moment is a International Metrology Resource Registry, where you can go to and say, if you want to get data about a particular material or material properties, for instance, you would be able to find it, and then you'll be able to download it. So a lot of it will be in the public domain.
Are the ontologies have to be standardized as well?
Well, yeah, well, that sort of. So it's only recently, in the last 5 years or so, that the NMI community has got to say, embrace this idea that the data we're producing has to be findable. And it's findable if you've got is storing it in a machine-readable way, and you've got the right metadata stored, and that is findable, and then you can download it. So, 5 years ago, nobody in the metrology community would understand what ontology is, but now we sort of do. So, there's progress there as well, kind of.
I also have a couple of questions, but I think in the interest of time, I'll move them to the panel discussion.
Okay,
later.
perfect.
Yeah. So
Thank you.
let's thank Alistair again.
Thank you.